Hey guys, let's do an example. So let's assume that we have the following system. So we have x dot is equal to this matrix A, where A is 2, 1, 0, 2. So this guy is our A matrix. And then we have plus B times U, where B is a 0, 1. And we have an initial condition. Let me pull up a pointer here. So we have an initial condition at t0 is equal to 0. And the initial condition is just at the origin, 0, 0. We want this system to be controlled to the point 1, 1 at time equal to 1. Okay, so I provided some steps in the last video on how to do this. So we're just going to run through those steps, and hopefully at the end we provide a controller that gives us what we want. So the first step is to find the state transition matrix. I'm not going to find that for you. I'm just going to list it out. But what we can do is we can use MATLAB to determine the state transition matrix. I think I mentioned at one point that there's a function called XPM, or exponential matrix. And then so you can define your matrix A, and then you can multiply it by t minus tau. And then this will give you your exponential matrix, okay? So note that we have, for this to work, we need to also do an SYMS, or symbolic, use a symbolic toolbox. And so we wanted to find a t and a tau, let's say. And then these symbols have to be real. Okay, so this is MATLAB code here. Okay, so this will give us our exponential matrix. And I'll just write out the exponential matrix for the system, but it is e to the 2 t minus tau, t minus tau, e squared t minus tau, 0, and e2 t minus tau. Great. All right, so then the next step is to compute our W, our controllability gramian, right? So we have 0 and 1, since it's the initial time and the final time. This will be equal to the integral of 0 to 1. Make sure that I'm writing this down correctly here. All right. So times the state transition matrix. Let me just write down what the equation is here. T tau, B tau, B tau transpose times the state transition matrix, tau d tau. This will be a 0 as well. Okay. So we have this guy. We have this guy. This is from the definitions of our system. Note that our system is not time varying, so those go away, right? And now let's input the variables here, or the different components. So 0 to 1, then we have 2, just rewriting the matrix here. 0, e squared t minus tau. And then b is equal to 0, 1. And then we got 0, 1 transpose. And then I'm just going to write the rest of it down here. Note that this will be multiplied, yeah. e squared t minus tau, t minus tau, e squared t minus tau, 0, e to the power of 2, t minus tau, and there. And then that transposed, still out of detail. Great. All right, so then this guy is equal to without going through all the computations, this should lead us to this matrix here, tau squared, e to the negative 4 tau minus tau, e to the minus 4 tau, negative tau, e to the minus 4 tau, and e to the minus 4 tau, d tau. All right, and so then after the integral, if we take once we take the integral of this should give us approximately the following: 0.02381 minus 0.05678, negative 0.05678, and 0.24542 after doing the integral. All right. And so then, we have our W matrix. So step 3 is to find this vector D. Find vector D, where D is equal to state transition matrix 0, 1 times xf minus x naught, right? So state transition matrix again is e squared t minus t naught t naught minus t due to the items here. So this is t this is t naught here, and this is t final here. And then where did our state transition matrix go? There. 0, 1, yeah. Let me erase this real quick, and I'll just input the 0 and 1 as I go. Bring that back up. Great. Okay, so this will be equal to e to the minus 2, 0, negative e to the minus 2, and e to the minus 2. Okay. Then our final state that we want to be at is at 1, 1, and our initial condition is the origin at 0, 0. All right, so then this will be equal to e minus 2 minus e to the minus 2, and then we get e to the minus 2 minus 0, 0. So you're evaluating e to the minus 2 is equal to 0 and 1, oops, 0 and 3.13534. Okay, so that's the end of step 3. Step 4 is we want to look at the controllability gradient from 0 to 1, and we want to multiply it by this vector A and make it equal to D. Okay, and we want to make sure that we can find such an A that satisfies this. Okay, let's go to the next page. So again, oh no. So I lost the connection here. Try again. Okay, so let's back up a little bit because I'm not quite sure where I lost it. So step 3 was to find vector D, right? And then once we found this D vector, we found D, and then step 4 was to we want to find A, where A is the solution to the gradient times A is equal to D, okay? And so I was just rewriting this here. A is equal to D, which implies that we get 0.02381 negative 0.05678 negative 0.05678 and 0.224542. Okay, and then this will be times A1 and A2 equals D, the D vector, which is 0 in the first element and 0.13534. All right, so we can rewrite this. And rewrite this as 0, oops, back up here, 0.2381 times A1, right? So now I'm just writing out these expressions here. So multiplying this A matrix into this W matrix and setting it equal to D. This will result in 2 equations. So I'm writing that here. So times A1 minus 0.05678 times A2 is equal to 0. And the second equation will be 0.05678 times A1 plus 0.24542 times A2 is equal to the second element of D, which is 0.13534. All right, so from the first equation here, we'll get that A2 is equal to 0.02381 over 0.05678 times A1. All right, and so this will approximately be 0.41934. I don't know why they go to so many decimal places. Times A1. All right, and so then we can take this expression for A1, A2 is equal to A1 and input it into the second equation. And then this will lead to A1 equal to 2.9336 and an A2 equal to 1.1.2302. All right, and lastly, with step 5, we want to take this A. We want to take this A here. So this will actually give us our value for U. For our input. So recall that we want U is equal to B transpose times the state transition matrix T naught T times A. So this will lead to, so this here, input our B matrix here, transposed at 0, 1. And then our state transition matrix is E. And the state transition matrix should be transposed as well. 0 minus T e to minus 2T. And e to the minus 2T. And then this times A1, A2. Okay, so once you do the computations to this, you then get a signal dependent on time, because note that time still shows up in the state transition matrix. So now you're going to have a time varying system, even though we started with a time invariant system, right? Just due to how U will be defined. So at the end of the day, we get U is equal to e to the minus 2T times negative 2.9336T plus 1.2302. All right, so this is how, just wanted to show you a method to get a control input given your initial time step and your initial state and your final time step and your final state. How to get a control value. Well, one, check to make sure that that it's possible for you to control your system from point X naught to point XF, but also to design that control value that takes you from that initial point to that final point. And then this ends up being the control signal that takes you there.